Hello everyone. We have been discussing digital modulation techniques for some classes now, and we will continue digital modulation techniques for some more classes. In the last class, we have finished some linear algebra background, which would be required from the future classes. So, in particular, we have in linear algebra we have seen what is a linearly independent set of vectors, what is a generating set of a vector space, what is the span of a set of vectors. We have seen that if the span of a set of vectors is the whole space, then that set is a generating set of the vector space. Then we have seen what is a basis. A basis is a set of linearly independent vectors which also generate the vector space. Then we have introduced the notion of length and inner product in a vector space, and we have seen the relation between them. We have seen that inner product of a vector with itself is the square of its length, and we have also seen that if we are given a set of vectors and if we want to find an orthonormal basis of the span of the set of vectors. So, if we are given a set of vectors, its span is a subspace of the whole vector space, and if you want to find an orthonormal basis of that vector space, that span, the subspace, then Gram-Schmidt orthogonalization gives a way to obtain that, a way to obtain an orthonormal basis of the span of a set of given vectors. So, we have seen example for Rn type of vector spaces, finite dimensional vector space over R, and we will just conclude this topic, this background of linear algebra with one example with signals. So, let us say we have, suppose we have, we will just do it with two vectors. Suppose we are given these two vectors, these two signals, say this can be V naught. So, this, let us say this is our signal f t, and we have, let us say, another signal 1 gt. So, these two are the vectors given to us. We want to get a set of orthonormal vectors such that these two can be expressed as linear combination of those vectors. So, the first thing we have to do, we have seen, is that we have to compute the first vector by taking this, scaling this first signal such that its length is 1. So, let us compute its length and divide by that length. So, what is length of f t? It is integration 0 to 1 square, that is equal to 1 dt root over this. So, this is root over 1, that is 1. So, our phi naught t is f t itself. Then we have to compute this. We have to take the second vector. First, we have to compute this inner product of phi naught with the second vector v 1. So, second vector is g t, second signal. So, we have to compute the inner product of this with phi naught. So, phi naught and g t. So, this is also function. So, this inner product is integration 0 to 1 phi naught t g t dt. Now, this integration is nothing but, this is just 1. So, it is this g t, just g t, phi naught is 1 in that interval. So, this integration g t dt It is the area of GT. What is the area of GT? It is base 1, height 1, so the area is half. So the second vector we will get by taking V1 minus this inner product times phi naught. So the second vector phi 1 t, second signal, will be, so GT minus the inner product times phi naught. So inner product is half times phi naught is Ft by the length. Now let us see what this is. So GT minus half Ft. Half Ft will be basically, it will be, half Ft will be like this. Its height will be half here. Half Ft. Sorry, this is half GT. Half Ft is this half. This is half Ft. Now GT minus half Ft. So this is half everywhere. The value is half from 0 to 1. So we have to subtract half from GT. So that means the axis will go up to this mid level. So we will get this is 1, this is half, this is minus half. So this is GT minus half Ft. Now we have to divide this by its length. So what is the length of this vector, this signal? We have to compute its length. So the length is that its integration 0 to 1, then GT minus half Ft square dt, then root over this. This is the length of this signal. So what is the length? Let us compute the square of this and then integrate. So what is the square of this signal? Square will have always positive amplitude. So here it will be 1/4 it will be like this, 1/4. Okay. Now, so you can see that integration of this whole duration has 4 parts. One is, this is 1/4, this is half, this is 3/4, and integration in each of these intervals is same. So we can integrate in only one part. Let us say from here to here we will integrate. So in this part we can say it is just like, you can shift it here also and integrate. It is like this. We want to find the area 0 to 1/4. This is 1/4. So this is basically, it is the square of t. This was actually linear square. So 0 to 1, it is t square dt. So t square dt. In 1/4 it will go to half, and that square. So it is actually t square by integration of this will be 2t, t square 1/4. So t square at 1/4 will be 1/16, so 4 dt. So we will have root over 4 t cube by 3. This is now 4 by 3, that is root 2, that is 2 by root 3. So now we have to basically divide this by this length to get the second vector. So what we have is phi 1 t is gt minus half ft by 2 by root 3, and that will be divided by, this will be divided by 2 by 3, 2 by root 3, that is root 3 by multiplied by root 3 by 2. So it will be root 3 by 2 here minus root 3 by 2 here, and it will be like this. Okay. Now obviously we can see that this itself, and as a result this also, is orthogonal to the first one, phi not t, that is this. And we can see, because we have divided by the length here, the length of this signal will be 1. So we have seen how to find orthonormal basis of the span of a given set of signals. This is a special case of the theory we did in the last class for arbitrary vector spaces. So we will basically use this particular technique later on, and we have to keep that in mind in several discussions later. Okay, so among the modulation techniques so far we have discussed PAM, PSK and QM. Now we will start another modulation technique called frequency shift keying. In frequency shift keying, the signals that are transmitted are of this form. A same sinusoid with same amplitude and same phase, but of different frequency are transmitted. So frequency is 2 pi delta f times m t for m 0, 1 to m minus 1. So here for m equal to 0 we will transmit cos 2 pi fct. For m equal to 1 we will transmit cos 2 pi delta f plus fct. So the frequency we will transmit for m equal to 1, for m equal to 0 will be we will transmit fc. For m equal to 1 we will transmit fc plus delta f. M equal to 2 we will transmit f equal to fc plus 2 delta f, and so on. So this signal can now be written also as real part of, this is the low pass representation, Sm t e to the power j 2 pi fct, where Sm t is root over 2e by t, this factor, and e to the power j 2 pi m delta f t. So, and this is of course a pulse which starts from time 0 to time t. Okay, so the low pass equivalent signal of the transmitted signal is basically this, and it is different for different m. Okay, Now we'll see a very special property of this particular technique. See what are the possible frequencies we can choose? Can we choose delta f as low as we wish? What would happen if we choose too small a frequency gap? So we will see that if we have too small frequency gap, we will in fact not do as good as if we have large frequency gap, that is delta f. So let us see. Let us see what is the inner product of the mth signal and nth signal. This is, we have discussed in the last class, that inner product of two signals is defined this way. So product of these two we have to take now. Product of these for m and n. So we have square of this, that is 2e by t. So we have 2e by t, and then cos 2 pi fc plus m delta f t times cos 2 pi fc plus n delta f t. Now 2 times this can be written as addition of these two frequencies, that is 2 fc plus m plus n delta f t plus the same thing with the difference of these two frequencies, cos 2 pi, difference of these two frequencies fc cancels, and m minus n delta f. Okay. Now what we have here is 2 pi times this. Let us just multiply this whole thing and write as 1 cos 2 pi is multiplied to both of this. So even before multiplying, we can see that the frequency of this signal, this part, is very high compared to this. So that means the period of this signal, this is a periodic signal with period very small compared to capital T. So this will have too many oscillations in 0 to t, like this. So its area will be almost 0, because every period will have area 0, and then at the end a very small part will remain, and in that very small part, which is less than 1 period, we will have a very small area. So this part will be almost 0, the integration of this part. So we can write this is approximately same as the integration of only the second part. So what is the second part? So only the second part is 2 pi m minus n delta f t dt. Okay. So this is because 2 fc plus m plus n delta f, because fc itself is very high. This is much greater than 1 by t. So this now is E by t, and we can see it is sine of this by this quantity except t, and then 0 sine of 0 is 0. So you will have only for capital T. So sine of this whole thing with small t replaced by capital T by this term except for t, 2 pi m minus n delta f. Now we can take this capital T here, then we can say this is equal to E sinc of x is nothing but sin pi x by pi x. So we have to remove pi and write sinc of 2t delta f m minus n. So we have seen here that the inner product of any two signals of the FSK signal set is this. Now it depends on delta f. If we change delta f, the inner product will change. So for what all delta f the signals will be orthogonal? That is a very special question, because we will see that for orthogonal signal set we can decode, we can do the demodulation very easily. So we will see now. For what values of delta f this will be 0 for all possible m and n. For any m and n, this will be 0. So that is true for what delta f that we want to see. So let us take m minus n equal to 1 first. The difference is 1. 1 or minus 1 will be same. So we take 1 or minus 1, whatever. So for that, it is basically the correlation. This inner product is basically E sinc 2t delta f for m minus n equal to 1. Now let us plot this. We all know the well known shape of sinc function. So it is 2t times delta f, is a function of delta f we are plotting, and because it is 2t, it will be 0 again at 0 at 1 by 2t, again at 2 times this, so 1 by t, then 3 by 2t, and so on. So minus 1 by 2t, minus 1 by t, minus 3 by 2t. So we will have sinc function well, this is symmetric. The way I have drawn doesn't look like symmetric, but it is actually symmetric. Okay. Now we can see from this plot that this value will be 0 at these places. So this is equal to 0 if delta f is a multiple of 1 by 2t. So if 1 by 2t divides delta f, this is a notation for divides. So this is 0 if 1 by 2t divides delta f. That means delta f is a multiple of 1 by 2t. And if 1 by 2t divides delta f, then it also divides m minus n times delta f. So as a result, this also will be 0 for any m and n if delta f is a multiple of 1 by 2t. So let us repeat that again. If delta f is a multiple of 1 by 2t, then this will be 0, as you can see from the plot. But if delta f is a multiple of 1 by 2t here, then this is 0, we know. And so if delta f is a multiple of 1 by 2t, then delta f times m minus n, this whole thing is also multiple of 0, a multiple of 1 by 2t. So as a result, this itself will be 0 for any m and n. So we conclude that we conclude that delta f, that FSK signal set is orthogonal if 1 by 2t divides delta f. So, the step frequency delta f, if that is multiple of 1 by 2t, then we have seen that FSK signal set is an orthogonal signal set. So, all the signals are orthogonal to each other. That is true if the step frequency is multiple of 1 by 2t. Okay. So, let us draw some example orthogonal FSK constellations. So, to draw the constellation, what should we do? We should find an orthonormal basis for the signal set generated, the subspace generated by the signal set. So, here we have all these orthogonal signals. So, only thing we need to do is we need to scale them so that the length of each signal is 1. Then that will give us an orthonormal set of vectors, because they are already orthogonal. So, we need to only scale them appropriately to have length equal to 1 for each of the vectors. So, we can say that phi I t we will generate so that they are orthonormal. So, phi I t can be taken as 1 by E xit. So, xit is given that we have constructed xmt basically. So, the mth, ith vector here, the orthonormal vector is, we just divide by the this is root e. So, that the length of this is 1 and they remain orthogonal. If you scale, they remain orthogonal. This is for okay. Now, let us take one particular example and plot the constellation. So, what do we have? Phi I, this phi for m equal to 3, phi naught t, phi 1 t and phi 2 t, this is an orthonormal basis. And we will express xits in terms of this and then plot. So, xit, this in this case, because we are considering orthogonal FSK signal set, xit will be nothing but root e times phi it from here. So, let us draw the points. So, this is this point is somewhere, let us say phi, this is say phi naught t, this is phi 1 t and this is phi 2 t. Now, xit is just a scaling of that. So, here there will be some point here, there will be some point here, this is x naught t, this is x1 t, this is x2 t. So, these are not the functions, but these are the components. So, we will draw only the scalars here. So, the components of this will be, as you can see, x naught t is root e times phi naught t plus 0 times phi 1 t plus 0 times phi 2 t. So, its coordinate is root e 0 0, this point, and this one is 0 root e 0. This point is 0 0 root e. Now, what is the distance between these 2 points? Distance between these 2 points is the norm or the length of the difference vector. So, what is the difference between this and this? This minus this vector, it is root e minus root e 0. So, the length here is root e minus root e 0. length of this, and that is root over e plus 0. So this is root over 2e. So this distance is root over 2e. Similarly, this distance also is root over 2e, and this distance also is root over 2e. Okay. Similarly, for two-dimensional case, it will have only 2 dimensions, and for m equal to 2. And remember here that the dimension of the signal space is same as number of points, 3 here. So for two-dimensional case, this is say phi naught t, this is phi 1 t, and here is one point, signal point, that is root e 0, and this is another signal point 0 root e. And for arbitrary m, what will be the points with respect to the basis vectors? For arbitrary m, we will have the points when we plot them. For two-dimensional, three-dimensional, we are able to plot this way, but for higher dimensional vectors, we will not be able to plot them, but we can easily see that their coordinates will be this. The first one will be just first coordinate root e, because x naught t is root e times phi naught t plus 0 times all the others. So root e, then 0, 0, all zeros. Then x1 will have only the first component non-zero, all others zeros. Similarly, x m minus 1 will be all zeros, then root over e. And you can see, verify that the distance from any point to any other point is root over 2e for orthogonal FSK signal set. Okay. Now, what are the properties that are obvious from this discussion? So, the properties of orthogonal FSK. One is that all the signal points have same energy. We can see that from these points, you can see that the square of the length, that is the energy of the signals, have the same energy, basically E. So, it is a constant energy modulation. Second, number of points m is same as the dimension of the signal space. That is the dimension of the span of the signals. So, that is number of points, signal points, is same as the dimension of the signal space. Third, what happens to the bandwidth utilization? If we want to increase the number of points in FSK signal set, what will happen? We need to choose more and more frequency. So, as a result, we will be using more and more bandwidth. So, as we increase m, we need to increase the bandwidth also. So, bandwidth increases proportional to m. So this is something very different from all the other modulation schemes we have used before. Previously we have seen PAM, QAM, then PSK. For all these modulation techniques, if you wanted to increase the number of points, we didn't increase the bandwidth. Bandwidth was same, but we are increasing either the energy of the signal set, average energy, by putting more and more points far from origin, or if you wanted to keep the energy, average energy same, we had to put more and more points near to each other, so that the probability of error was sacrificed. So here, to increase number of points, we are increasing the bandwidth. So this is another way. So but the distance will remain same, energy will remain same, energy is still E, and distance is still root over 2E, the distance between any 2 points, but we are just increasing the bandwidth that we are using. So we are actually compromising something or the other when we want to increase M. And so we can say energy and minimum distance. Minimum distance is basically root over 2E, which is same for all pairs of points. Minimum distance, both can be kept constant while increasing the number of points. But what do we compromise? Compromise bandwidth, as you said here. So compromise So if you want to increase the number of points, we will take more and more frequency. If this is the frequency axis, we first took one Fc, then Fc plus delta F, another point for 4 FSK we will have something like this band, and then we increase number of points, then we have to take larger band. So you are taking more and more bandwidth to transmit more and more bits per symbol. That's the idea. So the difference between this FSK and all the previous modulation techniques like PAM, QAM and PSK is this. The fundamental difference is this, that energy and minimum distance need not be changed to increase number of points. It can be done by increasing the bandwidth. Okay. So we will discuss immediately another very similar modulation technique called pulse position modulation. So here we have seen that in this case, for the case of FSK, we have taken different frequency for different symbol. To transmit different symbol, we have taken different frequency. But we can do the same thing in time also. We can take a pulse and transmit at different time depending on what we want to transmit. So this is called pulse position modulation. We will discuss the baseband version of that, but it can be easily changed, modified to have passband modulation. So it is basically the dual of FSK. In FSK we take different frequency, here we take different time. So if you have a pulse PT, so if you have a baseband pulse, it will be baseband. If you have passband pulse, you will have passband pulse position modulation. Here the signal set is this. What is the energy you want to transmit? That is E, and EP is the energy of the pulse we have taken, P T minus M delta T. So this is the signal set. What are we doing? We are taking a fixed pulse, fixed amplitude is not changed, whereas we are just shifting the pulse by different multiples of delta t. So let us take an example. If we take this rectangular pulse, say this is t by 4, we want to take 4 ppm, we want to have 4 points. So this is t, we want to transmit 4 symbols, 4 possible symbols in t duration. There is 2 bits in t seconds. So this is the pulse pt. Then for 0, m equal to 0, x0 t will be simply, m equal to 0 will give us simply pt times this constant. So we will have t by 4, this is x naught t. We will have, for m equal to 1, we will have t plus delta t. Now let us take delta t equal to t by 4. So this pulse will be shifted by t by 4. This is our x1 t. For m equal to 1, we will transmit this. Then for m equal to 2, we will shift it by 2 times delta t, that is 2 times t by 4, that is t by 2. So this is t by 2, it will end at t by 4 plus t by 2, that is 3 t by 4. And this is x2t, this is x3t. For x3t, it will start from 3t by 4, 3t by 4, it will end at t. So you can see that we are really just changing the position of the pulse to transmit the information. The information is contained in the position of the pulse, not in the amplitude, if it is passband, not in the phase, not in the frequency. Phase, frequency or amplitude of the pulse is same for all the possible values of m. Only the position of the pulse is being changed. So this is just like frequency FSK, where we change the frequency of the pulse. Here we are changing the time of the pulse. And you can see that this signal set is also orthogonal. You take any two, they are in different time, so their product will be 0 function. Product of say x1 and x3. This is non-zero only somewhere, this is non-zero at somewhere else. So product of these two functions will be 0. So the inner product of these two will be 0, and as a result they are orthogonal. So all these signals are orthogonal to each other. So this is another orthogonal modulation scheme. So this is also orthogonal modulation. And all the properties of FSK are still valid for ppm. Let us see, all the properties of FSK are still valid for FSK. Constant energy modulation. Obviously each has the same energy, because one is the shifted version of the others. So they have the same energy, and energy can be computed easily. Take the integration of the square of this pulse. M equal to n. This is again, dimension is same as the number of points, because they are all orthogonal to each other. You have to scale them appropriately to get the basis. You will get 4 basis vectors, orthonormal basis vectors, and constellation will be exactly same as just FSK modulation. Then bandwidth increases proportional to m. Now if we want to increase the number of points in ppm, how do we do? we want to keep the same symbol interval. So we cannot increase this time so that we put more and more time shifts. We cannot do that. We have to keep this t same, but then if we want to increase capital M to 8 from 4, in this case it is 4 in this example, but if you want to have 8, we have to take a narrower pulse. So the width of this pulse will be not t by 4 but t by 8. Then we can have 8 shifts. So it will be a half width of this, and then we can have 8 number of shifts of this pulse. Then we can transmit 8 possible values in this symbol interval. And what will that mean in terms of bandwidth? If you take a narrower pulse, the bandwidth of that pulse increases by, it actually doubles. So if we increase the number of points by 2, by multiple of 2, then we actually increase the bandwidth used by 2 factor. So we can see that bandwidth increases proportional to number of points m. And again, energy and minimum distance both can be kept constant while increasing the number of points. As we have seen, we are actually keeping a narrower pulse, and we can still keep the energy same by amplifying it, because we are taking narrower pulse. We have to use a bigger amplitude pulse so that its energy remains same. We can do that, and its minimum distance of the signal set also will remain same, but the bandwidth will be compromised. Because we are taking a narrower pulse, the bandwidth will increase. So we have discussed in this class frequency modulation, frequency shift keying and pulse position modulation, and we have seen that they are kind of dual to each other. One is in the frequency domain, taking different frequency depending on m, and another is in the time domain, taking different time shift depending on m. So they are dual to each other and they have exactly the same properties. Bandwidth can be increased to increase number of points, while energy and minimum distance can be kept constant, and bandwidth increases proportional to m as m increases. And the number of points m is same as the dimension of the signal space. So all these properties are true both for FSK and pulse position modulation, which is also called PPM, pulse position modulation, PPM in short. So in the next class, we will see some more modulation techniques. That's all for this class. Thank you.